Okay, good morning and good afternoon. I will start with the introduction as we have more participants slowly start to join the webinar. Okay, so today, welcome to the ACIGS webinar series, and this is our webinar number 36 of the series. And today we're very lucky to be joined by Eric Blond, and today he's going to be talking about designing with geotextile filters, ensuring the long-term performance and as a replacement to traditional sand and gravel materials. So if we progress to the next slide. Okay, a little bit of information about the IGS, the International Geosynthetic Society. So the IGS, it's a global network, and there's 44 chapters globally. So the Australasian chapter is one of those 44 chapters, and then within those chapters, there are individual members and student members, corporate members. So there's a large cohort of over 4,000 members globally that are part of the IGS society. For more information about the IGS, if you're not part of the society, you can join the website here at geosyntheticsociety.org. There's a whole host of information available on the website about how to join, a lot of information about previous events, future events, news. There's a fantastic sustainability section, so I do encourage anybody that's not visited the IGS website to take a look and have a browse through the site. There's a lot of information available on there. Similarly with the Australasia chapter, again, we've got our own resources available specific to our area. So here you can look at joining specifically the IGS Australasia chapter. We've got an event section. It's got a full library of our historic events and webinars that have been recorded, so you can access those through the event section. You can have a look at the news and upcoming events that we'll be hosting. Just an example there of the webinar library. So as I say, you can access all of those as part of being a member of the Australasian chapter. As I mentioned, upcoming events, here's just one of them. So we're pleased to announce the launch of GeoANZ2 after our successful first GeoANZ Australasian Geosynthetics Conference. So this will be hosted in Melbourne at the Crown Conference Centre next year between the 9th and 11th of July. If you visit the website at geoanzconference.com.au, we're now accepting registrations. You can submit abstracts and find more information about the speakers and the topics they will be speaking on. If you would like a certificate of attendance for today's webinar, please email info@acigs.org and we can arrange for that to be sent to you. And today's webinar, as I mentioned earlier, is going to be presented by Eric Blond. And here we've got a brief introduction about Eric. I will briefly leave this up on the screen. I'm sure a lot of you are aware of Eric and his work. He's done a lot of got a lot of experience in this area. He's authored many papers, and he's been pivotal in drafting ASTM standards and ISO standards on the topic as such. So we're very lucky to have him with us today. So thank you, and over to you, Eric.
Thank you. Do you hear me?
Yes, loud and clear.
Okay, so now I need to share my screen, and I will try to share the right one. Here we are. So you see my screen now?
Yes, perfect.
Okay, thank you. So thank you very much for the invitation and for the introduction. I should probably add that this can also be considered a technical committee on hydraulics joint presentation with ACIGS or with IGS Australia, I think is a new designation. But voila, okay, so let's start with this introduction of my goal here is to introduce the work which was done within ISO TC 221 on geosynthetics within the working group 6 on design, and there is a subgroup which was focusing on geotextile filtration, on the design of geotextile as filters. So here I will introduce to you what has been done in this standard at the end. And this is packaged with the environment that we have considered to as a guidance for that. So, okay, first thing first, we want to use geotextile for filtration and drainage, but why do we want to do that? The primary goal of this application is to have proper water management in soils. And I think it's important to remind that for everybody, because any structure can be designed as well as it can be. If there is excessive water in the structure, it's not going to work. Positive pour pressure can reduce the bearing capacity of soils. It can bring some other change in soil properties. Presence of free water, of excessive dampness near the foundation of a building can bring molding problems in buildings. It will affect the crop production in agriculture, etc., etc. So there is many consequences which are caused by the poor management of water in the soil in different environments. So first example, a very bad example of an undrained and unpaved road built on fine-grained soil. This is a total disaster. You cannot basically use the road anymore. And if we were looking at the same road when it's dry, this dry soil would offer a good driving surface, except when it's completely damp, wet, it does not have any shear strength anymore. This also works with paved structure. Here you have on the left-hand side a cracked road, a cracked pavement. When this cracked pavement will receive rain or snow melting, in the case of Canadian weather, this snow melting or this water will penetrate within the cracks, will saturate the soil underneath. If we have some frost, it will crack the frost will expand, it will crack the asphalt even further, and that eventually creates those very nice potholes that we are very well used to in the Montreal area. Now, if we go back to a more universal environment, a typical application of geocomposite drains is the capping of landfills, of waste, of confined waste material. And on these caps, we have a liner which avoids penetration of water, of rainwater, and the water must be drained. And if it's not properly collected, it will saturate the soil, and this saturated soil can slide, or it can be eroded and go down the slopes. Retaining walls, if we have a saturated soil behind a wall, that will affect the coefficient of earth pressure, and that may require much higher strength of the reinforcing components. And this is usually not what is considered in the design, which means it can lead to failure of retaining walls. That's actually the most classical cause of failure of a retaining wall, is inefficient drainage that will essentially push the wall away too much compared to the resistance of the geoscientific components. Internal erosion now is another critical aspect. Sometimes you can have some drainage which occurs naturally, but if you don't protect the soil from being eroded internally, the soil can be displaced with the water, and without an effective filter, you can have cavities being created in the soil, and eventually that leads to failure, such as the one we see here. This happens, I have to say, periodically in Montreal. We have, well, Montreal is a very nice city to live, but the infrastructure are getting old, and like everywhere else, aging infrastructures need attention. So a typical, I've seen actually, I would say, I've seen about 5 of these. So it's not exceptional in the last 20 years. So these are coming from the water infiltrating through the road or leaking through a water pipe and eventually being collected in a sewer. This transports fine particles into the sewer, and this creates cavity which eventually open up. So these can be several meters below grade. So such sinkholes are another evidence of internal erosion within the soil, which could be prevented by installing geotextile filters or filters in general near the regions where the water is going to be collected. Internal erosion, the most dramatic applications are probably the one that we're going to see now in the dams. So when you build a dam, you typically have a structure through the dam. In that case, you can see that these structures did prevent proper compaction of the soil near the structure, and that created an opportunity for the water to leak through these discontinuities, which have a higher permeability because they are not as compacted. And eventually that created this dramatic failure that you see here, which requires the complete reconstruction of the dam. Massive failure. Another scary situation is this canal, which was built on top of a dam, of an embankment, and no drainage was installed, or an inefficient drainage was installed under this structure. So with a small leak, and actually any leak would have created the same. It's not related to the lining material, it's really a drainage problem. A leak through the structure here eventually created a flow from the canal to the edge, and that eventually created the dramatic failure that you can see on the right-hand side here. You can see a video of this on LinkedIn. That's where I took these photos. And there is, if you're going to find the link on my LinkedIn page somewhere in my comments. So at the end, structurally sound geotechnical structure cannot last without adequate water management. And this is true with essentially every geotechnical structure, starting from a roadway, veneers in landfills, retaining walls, embankment, dams, canals, etc., etc., etc. There is not one structure that will not be affected by an excessive excess water within the structure. So historically, we've been using granular filters and permeable material as drainage mediums. And this is working very well. Practically, efficient drainage solutions have been used in man-made structure long before geosynthetics were invented. We can see here a 2,000-year-old road near Rome, which is a place where we're going to have our next international conference, by the way. And these structures can last very, very long. So here you can see, obviously, a well-designed and well-built structure. You see the stone, which is 2,000-year-old, which can last for another good duration because everything is perfectly stable. However, we should keep in mind that aggregates with adequate quality for construction are probably the less renewable resource on Earth. People are focusing a lot on oil and petroleum products as a non-renewable resource, but in fact, aggregates are less renewable than oil. If we're looking at the geological scale or whatever reason. They are less renewable because we need them where close to the locations where we're doing construction. So here, another example near my home, near Montreal, that's a mountain which is about 20 kilometers from Montreal. And you can see here that it's been, a quarry has been developed about 50 to 60 years ago, if I'm correct. This quarry is taking material here to build roads and so on. On the same mountain, on the same footprint, you have a ski resort. You have a residential area with a couple hundred houses. You have a natural park here with protected wildlife. And all that is on the same 10 square kilometers footprint. So if we look at that from a sustainability perspective, this cannot last very long. First, it makes no sense. We have at the same time, on the same piece of land, protected wildlife and a quarry. This is not appropriate. If we project with what we see here, how long we have left of stone, even if we forget about everything else, the stone is the most important. This was 50 years. There is clearly a limited number of years that remains here for to build more roads, to build more concrete and structures and so on. So using stone, as we've been doing in the past, simply is not sustainable. In Montreal, on the island of Montreal, we have another quarry which is already empty. So right now we need to truck the sand and gravel from 30 to 50 kilometers away from downtown to bring any sand and gravel into Montreal. 30 to 60 kilometers away is a long distance. And when we are done with the next mountain, it's going to be another mountain even further. It just doesn't work. Another interesting example is Burj Khalifa tower in Dubai. This is 110,000 metric tons of concrete. And to be able to build this almost 900 meters high tower, of course, you had extremely strict requirements for the concrete, for the aggregates, for every materials. And the only type of aggregate that would be available, that would be able to deliver the right engineering properties for this concrete, is coming from Australia. So congratulations, in Australia, you have the best material available. But again, this is not sustainable. What does this mean at a different scale is that we can probably count on a couple of hands the number of Burj Khalifa towers that we can build on Earth through the course of mankind. So that's very limited. Voila. And let's not forget that Dubai, in principle, is sand. It's sand everywhere. But it is not the right sand. It is a sand which does not have the engineering properties that we need to build this fantastic concrete, which allows us to build a 860 meters high tower, I think I remember. So that's really the problem with aggregates. We think there is a lot. If we look outside, there is a lot of dirt, soil, and so on. But the fraction of these materials which have the right engineering properties is very limited. So we need to find alternate. We need to find ways to use the materials that we have in an exact location and preserve high quality aggregates for other purpose. So again, we have this situation where we have this road in Italy, 2,000-year-old, as mankind, in fact, has millennia of experience with sand and gravel. It is very durable. It is taught in every university. And we have this problem of limited capacity, limited availability. Now, my question is it so important to have an infinite service life for sand and gravel, for the drainage or filtration materials that we're using in our structures? Let's look at our needs are changing. And let's look at the same road. It's a different view, but it's the same road. We have this road, which is very nice. It's been there for 2,000 years. We can have a car driving on this road. But this is more like what Rome looks like today. This photo comes from Rome as well. This traffic would never, ever, ever go through that road, even delayed by many hours. It simply doesn't work. So this road does not exist anymore, and it cannot be valued in any way. So that means we've used an eternal, infinite durability material for an application which is a short-term application at the end. This 2,000-year-old road is not used for transfer of people anymore. It's a decoration at the end. If we build on this avenue here the same quality of road with eternal construction materials, this is going to be eventually obsolete. Because our needs are constantly evolving. The number of users, the growing population, the weight of vehicles, it has become heavier and heavier. The speed, we have less tolerance on the irregularities of the surface. And now the next steps is electrification of transport. There are more and more projects where we're putting the energy resource within the structure. So that will affect also how we design and we approach these structures. More and more people are using public transport and alternative transportation means, bike, walking, etc. I heard about drones coming up. So all these basically makes that we have no idea what our needs are going to be in 50 years. And preserving short design life for infrastructures is very realistic. So on the long run, I think the strategic choice of construction materials will be driven by the performance and the cost, because this will always be the case, and by the carbon footprint and how we are using our resource. Practically, we see many promises here and there at the political level, and this will eventually come into regulation and so on. So speaking of carbon footprint, it's important to realize that despite it is a plastic-based material, the carbon footprint of geosynthetics is in fact much lower. I will not go through all the details here, but overall, it's important to do the analysis from cradle to grave. So for a given function, whether it's filtration, drainage, or anything else, we need to assess how much energy, how much carbon we have produced from the beginning of the establishment of this function on a project to the end, which means putting everything back after demolition and after giving back to nature the structure. And doing this analysis is, there is, by the way, here in the bottom of my slide, a very good paper by Raja in 2015, so this is not new science, which defines relatively well how to proceed with those things. And I highly recommend to visit those things if you're interested by that. An example with numbers that I could find, which I thought was interesting, was for multilinear drainage geocomposite in France. So this analysis was done in 2011, and the numbers they calculated would show reduction of carbon footprint by anything between 25 and 87%. So we're at something close to 8 times less carbon spent with using geosynthetics compared to using gravel. So this is elaborated analysis. The very simple thing that we can do is look at how much trucking is needed. A truck burns gas, and when trucks will be electric, they will still burn gas because at the end energy is carbon. This truck on this photo is carrying 16,000 square meters of a geogrid. It would be a similar quantity if it were a geotextile filter, by the way. And if we consider that this material will replace about 300 millimeters of sand and gravel, this single truck is equivalent to almost 5,000 cubic meter of imported gravel. And if we're in an urban environment, we need to remove whatever we are taking from out from the soil. We cannot build and increase the height. So which means for every quantity of material which is imported, we have to remove a similar quantity of material. Long story short, one truck of geosynthetics will be equivalent to up to 500 trucks if the geotextile or geogrids can be proven to replace 300 millimeters of granular material. So it is, from there, it's not necessary to do much more calculation. The benefit is huge. In fact, it is so huge that in 2014, the US Senate has developed, amended the Water Resource Reform and Development Act, which dates from the early 70s, and has named geosynthetics as well as composite and I think is roller compacted concrete, the third technology, as innovative technologies that should be considered by the US Army Corps of Engineers and the engineering community for constructions, in construction. So at the end, if we look at the geotextile filters and geocomposite drains versus aggregates in civil structure, the future is bright. It is bright considering their low carbon footprint and the essential need of to preserve a limited quantity of granular materials that we have globally on Earth. So in fact, there is a discussion about the availability of water. Water is indeed a critical resource for mankind, and it is getting scarcer and scarcer. But water, there is more water than there is sand and gravel for construction at a reasonable distance from where we need these materials. So now we're going to focus on the use of geosynthetics to manage water in soils. First, we need the first function on which we're going to focus today is to prevent internal erosion, and that is the filtration function, which is delivered by geotextiles. It's important to make the difference. Some people don't speak of membrane, for example, and membrane is going to cover anything that is plastic or fibrous. So we're really speaking of geotextile as a right word for the product that will deliver the filtration function. Other than that, we can remove water from the soil and offer the drainage function, which is a different function. The drainage function is not the filtration function, it's a different function, and that will be completed with a geocomposite drain. The filtration function is the main goal is to prevent internal erosion of the soil. So what we mean by preventing the internal erosion of the soil is we need to retain the soil skeleton. It does not mean that we're going to retain 100% of the particles. We're retaining only the soil skeleton, which is a coarser fraction. The coarser fraction through which a stress is transferred. So if you have a mechanical stress, a pressure, which is on top of the soil, this stress will travel through the soil and eventually reach another component of the whatever is under these layers of soil, and this transfer of stress will go through the skeleton, not through the finer particles which are potentially movable within the skeleton. Secondary function, secondary goal is to let the water pass through the plane of the geotextile, of course, to prevent building up of pore pressure upstream of the geotextile. If we look at how the modern technologies were developed, this comes from agriculture in the 19th century. Before that, it would, of course, be done, but the way we approach drainage and filtration really comes from the 19th century. And a gentleman named French has published a paper where he has described how water can be removed from fields and how that is going to improve crop production. And so he has defined that the drainage efficiency is based on the contrast of permeability between the drainage media, which must offer a much higher flow capacity, and the soil to be drained. So that's really how things have been done. In the past, clay tiles were used to capture water, to transport the water. Now it's polyethylene pipes wrapped in a geotextile filter, but at the end, it's pretty much the same as what we were doing in the mid-19th century. So this is a photo of Mr. French. And for those who thought Mr. French, the French drain was coming from France, I have an interesting anecdote. Mr. French is the father of Daniel Chester French, who is a sculptor. And this gentleman has made the Lincoln Memorial. So if anybody can be more American than Mr. French, I would like to know that person. Mr. French is American, definitely. Nothing to do with France. Maybe some of you recognize I have a little French accent. So no, when we use a geotextile in a French drain with a contrast of permeability, we're going to install this geotextile between the soil that must be drained and the high flow component, the high permeability component of the French drain, which can be gravel, which can be a pipe, etc. So that the geotextile will help maintain the contrast of permeability between the soil and the high flow component. Another application which is interesting to expose is geotextile filters for bank protection. Here we try to retain the soil skeleton again, but we want to let the water pass through the plane of the geotextile at any time in the year, of course. So the direction of flow, what's interesting that the direction of flow will depend on the season. In springtime, there is potentially more water in some region in the river or elsewhere, depending on the water level in the river. And so the direction of flow may change depending on the season and the respective level of the water in the soil and in the river. In that case, The geotextile filter is going to be covered by riprap, which provides confinement, mechanical stress on the fabric to prevent it from being removed. Mechanical protection against ice, for example, maybe not so much in Australia, but in Quebec, in Canada, for sure. UV protection that you do have in Australia, etc. So that's really a different approach to filtration. Other interesting application for filters in a earth dam. So here we can see the geotextile being used as a complement to soil filters. You can still see the core of the dam, which is here, which is clay. You can see the geotextile right next to it, protecting the clay from being displaced from erosion. Then you still have the geotextile behind the clay. You have a fine gravel and a coarser gravel. So that's really by the book, where the D85 is going to be, of each layer is going to be selected against the D15 of the next layer. And that is one other application which is going to prevent those failures to occur. Valcroze Dam in France was in fact the first application of a geotextile filter in a dam. First, it was used on the upstream zone under the riprap, so that's really on the top of the top layer. You can see here on the cover of this magazine the geotextile which is installed, and on top of which the other granular materials will be deposited. And it's also been used on the downstream drain. So you can see here the limit of where the embankment is going to be eventually. And you can see the geotextile filter, which is on top of the finger drains, which are there. This was a 17 meters high homogeneous dam. It was included, so those slides, by the way, I have to acknowledge they're from JP Giroux, who accepted that I use his slide. Adaptation of the text is mine, but the slides are JP Giroux's slides. JP was the design engineer for this dam, and he was not able to get adequate sand filter for this particular location. So again, scarcity of granular materials in a given region, and that was in the early 70s. So he elected to use a non-woven geotextile, which had never been used before as a filter. So it was an innovation from the 70s. The dam has been in service since 1970, so that means it's already 53 years old and still in place and still in good condition so far. This dam, of course, is monitored, and so is the geotextile filter. What has been observed? Constant trickle of clean water. The flow rate, which is measured, is consistent with the properties of the soil used in the embankment and the water level upstream, etc. So there is nothing surprising. Everything works as planned. There is no seepage of water that was ever observed through the downstream slopes. So that means the drain is working well. If the finger drains in the bottom of the slope here were not working, water would eventually seep through the slope, and that would be potentially a disaster. And of course, samples were extracted after some time. It was the first application of geotextiles in such a structure, so they were very careful and monitoring was done as it should. Sampling were done after 6 and 22 years. No deterioration of the materials. The geotextile filter was in perfect condition with negligible clogging, with less than 0.2% of the pore volume. Again, other application in dams, and in pretty much all cases, the geotextile is going to be used as a replacement for sand. Important remark for filtration is a separation. What we want to do when we do a separation layer in a structure, we want to avoid mixing of the imported gravel with whatever subgrade is underneath. If the subgrade is mixed with the gravel, we have a percentage of clay or fine grain material within the gravel on a given thickness of gravel, and this gravel will behave like the underneath material. So if you put 10% of fine grain material in a gravel, the D10 of this gravel will become a dimension of particles from the fine grain product, so will become the permeability of that material. So only 10% is enough to damage the engineering properties of the gravel and hydraulic properties. So filtration is an important function for the geotextile used in separation. However, what we observe is that the design for filtration has been extremely simplified by local authorities. If I take the example of H2 M288, now the requirement is a maximum of 600 micrometers for the opening size. That means essentially any geotextile. This is actually working well for separation, but I want to emphasize on that. Maybe separation is not a critical application for filtration. It is for filtration design. It is a critical application for filtration. If the water is blocked at the level of the geotextile, you will still have water pockets under the fabric during installation of the gravel layer. And you will, in the long run, have water standing on top of the fabric. It is not what we want. But in terms of service, we have minimum quantities of water circulating through the geotextile, and therefore it is not critical. So I want to emphasize on that. It's not because separation is not a critical function and a critical application for filtration, geotextiles, that this approach can be expanded everywhere. This is strictly limited to the separation function. Now I'm going to go through very quickly a variety of applications of geocomposite drains just to show where geotextile filters are used, and because it's important. So geocomposites are typically a combination of a drainage core and a geotextile, and we have several different type of structures. Here we can see in infrastructure, we have fabrics, geocomposite drains, which are preventing water from entering from the side and also collecting water, infiltrating through cracked pavement. Here we have a product which is installed on the subgrade to capture potentially rising water table and avoid it would go through it would soak the foundation, saturate the foundation. And another application which is interesting and which makes, again, geotextiles being the prime product, it's very difficult to better. It's retaining walls. Rigid retaining walls. We have a concrete structure which was built. We need to capture the water on the upstream side of this wall. And it would be extremely difficult, if ever possible, to do it right, to install a granular layer here. So geocomposite drains will be the best solution, and therefore geotextile filtration is a critical aspect. Here, a reinforced soil structure. We can see here the layers of drainage composite in the back. Prefabricated vertical drains. Here we have a short-term application, in fact. All the previous applications that I've shown before are long-term applications with design lives which are in the 50 to 100 years or more. PVDs, typically, we're happy if the geotextile ceases to work after 2 years, 3 years, when the soil has been consolidated. When it has been consolidated and it has reached the density that we are looking at, we don't want it to continue to consolidate. So in those cases, it's actually one of these applications where short service life are considered for geosynthetics here. In landfills, we use geosynthetics and geotextiles in gas collection layer, leachate collection layers. On the base, we have secondary drainage layer for the leak detection, and we can sometimes use them as a complement to the primary drainage layer. It is not always accepted in every regulations, but it is an interesting way to reduce the thickness of the granular layer, or to weaken the requirements for the primary drainage layer in the base of landfills. So At the end, when we are thinking geotextile filtrations, what's important is we have a very wide variety of surface conditions. It's not one application fits all. We have several different applications, in fact. We need to look at the type of soil in contact with the geotextile. Is it going to be a soil or a slurry, by the way? I'm not touching slurry in this discussion because it's a different fish. The flow of liquid, which is important. Is it an occasional flow? Are we going to have a few drops of water here and there, or is it something permanent where we have to expect the filter to be exposed to a flow of water all the time, like in agriculture, in retaining walls, in bridge abutments, in dams? The geotextile is permanently exposed to a flow of liquid, but maybe not for separation, for example. Maybe not for situations where we expect the water table to rise up and down once a year, sometimes, etc. So the flow conditions are very different from one application to the other. Type of liquid. If we're draining liquid water, will there be any suspended particles? Are the particles going to be captured by the soil, which is upstream of the geotextile, or not? Shall we expect these fine particles, suspended particles, to reach the geotextile? Will there be organic or chemical activity? Like if it's a landfill, a leachate will generate its own set of problems. If we have a mining structure with a heavy brine, which is likely to create precipitation near the filter, that's another set of problems. Are we in a soil which is prone to iron clogging, or manganese? Do we have iron or manganese oxides which can precipitate on the geotextile? All these things must be understood. After that, we have, of course, mechanical stress. We need the geotextile to survive the installation. We need to assess what is the impact of a failure. That's actually a very important aspect, because accepting that the water is going to flow in 3 hours instead of 1 hour is sometimes very reasonable. While if we have pore pressure developing on the geotextile surface, and this pore pressure can affect the stability of the entire structure, like a veneer on a landfill, for example, on a landfill cap, this will have a tremendous impact on how we're going to approach the question. Installation condition, and we'll see after, if there is a rain event between the installation of the geotextile and its covering by soil, that is a recipe for disaster, actually. You can have soil particles eroded and covering the geotextile, and that will create immediate clogging of the fabric, and it's not going to work. And after that, service life. What do we expect in terms of service life? As I said before, PVDs, we typically expect a couple of years of a service life. Landfills, I consider that a couple of years as well for the base of landfill. For the capping, it's a different story. But for the base, for primary drainage layer, it's essentially the short duration during which we are filling the landfill. After that, there is no liquid arriving anyway, or little liquid, etc. So, and the service life can be also very long-term if we have transportation infrastructure. So that's really, all these conditions must be considered when designing a geotextile. So we can enter now what was done in the ISO work. So basically, you can obtain this document directly from ISO. It's you can see on the right-hand side here what it looks like. It's a technical report. It's not a standard. It's a design. It's a technical report providing information on how to design using geotextiles for filtration. So we explain in this document what are the concepts and fundamental principles, and that, as I said before, the long-term performance will be achieved when the geotextile offers the following performance, which are to retain the soil skeleton while letting the water pass perpendicular to its plane, and Another aspect which must be achieved is survivability. It must present sufficient mechanical properties to resist installation. It must also resist mechanical stress which are going to be suffered during the service life. And finally, we must use a polymer which is adequately formulated and which is going to last long enough. For example, I've seen situations where polyester geotextiles were used in mining environments. They were first interesting for some aspect, for the small opening size, but they dissolved. They got dissolved completely because it was not the right type of polymers in this particular environment, which was very basic with a high pH. So, but that's lesson learned, and voila. So, yeah, one aspect which is important. What's happening here? I'm lost. Okay. Soil skeleton, I've explained that before. The designing for filtration, one of the core hypotheses which is considered in the design is that there is an intimate contact between the soil and the geotextile. And that's very important. And that's going to affect the way the structure is approached, the way it is installed, because we must have this intimate contact. The typical example is the situation where we have a geotextile which is installed on the pipe, on the perforated pipe, and backfilled with gravel. Some people think, oh, I'm putting double protection for my pipe. I have this geotextile fabric and I have the gravel. Everything will be perfect. What is actually happening here? What's happening is that the soil, which is not compatible typically with the gravel, is going to slowly flow particles by particles up to the geotextile. And in fact, what we're having here is a slurry, which is filtered by the geotextile, and that will not work. So the intimate contact starts there. The geotextile must be in contact with the soil which is drained. The second typical example is poor compaction. If you have a geotextile installed in a structure on a wall, and the backfill is done with a fat clay or something like that, and you have cavities everywhere, when water reaches these cavities, it's going to transport small particles, and these small particles will be a slurry arriving on the geotextile, and that will clog the geotextile. So it is very important to understand the significance of intimate contact between the soil and the geotextile. That is the primary cause of failure, in my opinion, in my experience. It's the primary cause of failure of geotextile filters. It is a lack of contact between the soil and the geotextile. Another thing I want to say, I've mentioned before no, here I've not mentioned, but it's here. The core of the ISO 18283 is based on the Canadian Geotechnical Manual, modified by Haybaum from Germany, and which has been found by the ISO TC221 group as the best information available. And I will add to that the most consensual information. The truth is that there are other design strategies which are available, and one of the very important one is Giroux approach to the geotextile filtration, as he has exposed in the Terzaghi lecture. This solution was not retained by the group for a variety of reasons. One of them being the way he creates approximation of soil properties, which leave space for discussion. But at the end, when a project requires an in-depth investigation of the filtration phenomenon and the design of a filter, I highly recommend to consult Giroux's work as a highly valuable addition to complete the design for filtration. So now we're getting into the detail of the opening size and so on. First step, when we're doing the design of a filter, confirm the intimate contact. Second step, exclude excessively critical condition. Ferrous iron or manganese oxide must be in very low concentration. There is no solution so far, not that I know, to allow these minerals to be in presence of a geotextile without clogging of the geotextile on a short term. And short term can mean 6 months, 2 months, 2 years, but it's not going to be 20 years, for sure. So in presence of this type of product, you have to expect some maintenance, some replacement of the geotextile filters. Organic matter, same thing. It's typically not going to go well. If the service life is short enough, that can work very well. After some time, we don't care if the system is clogged, fine. But if it's a long-term project with organic matter, it's not going to work. Dissolved mineral, if there is a risk of precipitation on the geotextile of dissolved mineral because of a change of temperature, change of pH or whatever, this also can be a no-go for geotextile. So far, there is no solution for that. Suspended solids in water, same thing. Suspended particles arriving on the geotextile fabric will adhere on the fiber and will clog it. These situations are considered too critical for use of a geotextile and requiring some preliminary treatment of the water of the solution or strategies for maintenance and replacement, periodic replacement. So after that, once we have excluded these two critical situations, we collect the soil properties and we go through the design. First thing first, everybody knows that retention criteria. What is the maximum dimension of the opening size of the geotextile? And the ISO guide is not proposing a dominance on AOS, FOS in Canada, O90 in Europe, or any other opening size. It's a generic approach which piggybacks on local codes and practice to propose a solution. So the opening size would be defined as a constant value multiplied by an indicative diameter of the soil. And this indicative diameter of the soil will depend on the type of soil. If it's a gap-graded soil, it's going to be typically the largest dimension of the gap, etc. So, and there is a non-retention criteria of fine in suspension. So we have the retention and the non-retention. The non-retention basically says we need to have a minimum opening size to prevent clogging. So we need to retain the soil, and we need to make sure that the fine particles pass through, so the geotextile will not clog with the fine particles. And we have a permeability criteria where the geotextile must exhibit a sufficiently high permeability compared to the soil properties and to the hydraulic gradient which is expected. Sorry. So for each of these criteria, you can see that an intrinsic property of the geotextile is compared to properties of the soil skeleton or the soil. And voilà, exactly. So first criteria, the retention criteria for the soil skeleton, where the opening size must be lower than B times DI. And you can see that in the document, I'm not going to read everything, but in the ISO standard, you have the exact description of what this property, what these values should be. In case of a silty soil of sandy with little silt soil, or more sand and less silt soil. So voilà, I'm not going to go through the detail, and I see that the time is running. So I'm going to skip the example as well and go directly. This is going to be in the slide you have available. You will have available. Non-retention criteria is going to be where the opening size must be greater than a constant by an indicative diameter of the soil. And in addition to that, for woven geotextile, we add a minimum percent open area, which is the surface of openings compared to the entire surface of the fabric. So again, an example that you can review eventually in the slides, which explains how to get there. Permeability criteria, velocity index. In the ISO world, we speak of velocity index. So this velocity index is in fact equivalent to the permittivity. It's the velocity of the water passing through the geotextile under a waterhead of 50 millimeters. So basically, it can be calculated considering the permittivity and the waterhead and the 50 millimeters. So this, in that case, here the velocity index must be proportional to the velocity of water that would arrive on the geotextile, multiplied by a constant, which is going to be 3 orders of magnitude for high risk application, 2 orders of magnitude for low risk application, and 1 order of magnitude for very low risk. If you think, for example, of a sports field where people play soccer, we design the structure so it can be free of water after 1 hour. But maybe if it's after 5 hours, people can wait before they play soccer. So it's that kind of consideration that makes this value being highly variable depending on the application. So again, some examples that you can review eventually. Additional properties of interest for geotextile filtration. One is a resistance to water penetration. In the early days, some manufacturers were using hydrophobic oils on geotextiles, or some surface treatments would not be prone to drag water through, to let water pass through. And I've seen situations where you needed to have up to 15 centimeters of waterhead on top of a geotextile before any water gets through. So you could basically take a frame, put a geotextile in it, and add 15 centimeters of water, and not a drop of water would pass through. As soon as you touch your finger on the fabric, you help the water pass through, it all goes down in one go. But that is a problem because that will affect the performance of the geotextile. And therefore, there is a consensus that we need to have a maximum maximum resistance to water penetration. And in fact, I think the recommendation is to have 0, which is easily achievable with modern technologies. But still, it used to be a problem. Another properties of interest is the number of constriction. So this property applies to non-woven geotextile. It's important to realize that it does not apply to woven or to knits, and it's describing the number of constriction or passage between fibers that the particles can cross while traveling through the thickness of the geotextile. I spare you the detail on the calculations, but essentially it can be calculated based on basic properties of the geotextile. There is even an ASTM standard, which I'm not referencing here, which explains, which provides guidance. Oh, here, yes, D7178. I actually wrote this standard, but it explains how to do the calculation based on thickness, polymer density, mass per unit area, and a couple of things. So what is the number of constriction? For a given random and isotropic distribution of fibers, the thicker will be the geotextile, the more chains for particles are to be retained on the constriction. So if you have a flow of particles here, you can consider that in a given plane, you have a distribution of constriction, which are basically the different paths through which particles can go through. And when you cumulate all these constriction that can be met on a given path, you are going to have a distribution of particles that will be the distribution of constriction through the fabric. So that gives an additional property which qualifies a non-woven geotextile with respect to the filtration. I spare you the detail. Actually, I'm out of time. In general, what the theory about constriction has shown is that the higher the number of constriction, the higher the chances of piping, the lower the number of constriction, and the higher the change of clogging. So for the similar opening size. Giroux also recommends a number of constriction greater than 25 to maximize the reliability of the filter based on the theoretical relation between opening size versus fiber diameter and thickness versus fiber diameter. I'm going to go quickly on this given the time, but long story short, there is a commercial component to this theory, which is absolutely valid from a theoretical perspective, and therefore there is no absolute consensus in the industry about if it should be specified always or not. There is no consensus. So, and more research should be conducted to basically confirm the relevance and the proposition above here. So next step for geotextile filtration is survivability. The one thing which is important for geotextile and which does not exist with soils and soil filters in particular is the tensile strength. A geotextile has a tensile strength, is capable to elongate with minimum impact on the opening size for non-woven geotextile at least. So this is something which is very welcomed. But still, it must not be torn. National codes are typically defining minimum requirements for the mechanical properties of geotextiles based on local practice, because these properties will depend on the type of equipment used, on how the other aspects of a project are dealt with, and therefore it's important to refer to national codes and practice to define the minimum requirements for survivability. In the US, the most known is AASHTO M288, and I think it's international. It's been adopted in many, many places, but not everywhere. In some regions, it's a different set of rules. One aspect which is interesting is the impact of the elongation of the geotextile. I think covering such rocks with a geotextile is not very typical. So here, in this application, which is a bit extreme, we can see that the non-woven is performing very well, while the woven did not resist installation. In most applications, it's not going to be that. We should not expect such critical conditions, but they're still, in terms of principle, it's interesting to know that the properties will vary with the application and the type of geotextile and the environmental service. Slurry filtration, as I said, I am not covering this topic really because it's completely different. A slurry is a mixture of solid and liquid. There is no significant contact between particles traveling in the fluid, and each particle is reaching the fabric, is isolated, and a cake will build up eventually. What's important to remember is that the filtration criteria that we use for soils are not applicable to slurry filtration at all. Clogging will depend on gradation of the soil, solid content, on several factors like that. And another aspect which is important is that in those applications, the performance is very often defined as 100% retention or close to 100% retention. And therefore, it is a contradiction. It takes to break the cake building up upstream of the geotextile to let the water flow because it's clogging all the time. So it's a different approach. And that will be the end of, the lab. I will first, I'm not covering drainage today, designing for drainage of geocomposites, but I want to remind those who are interested that I have made a webinar on this topic in April 2020, so that's a bit more than 3 years ago. And it's available on the ACIGS webpage, and it's a 1-hour webinar on the design of drainage materials. As a concluding remark, geotextile filters and composite drains are typically better than gravel with respect to consistency and performance, constructability, try to build a vertical wall with gravel, versatility, you have a very large array of products available. They are more sustainable for a variety of reasons. First, availability of natural resource. We have a limited quantity of gravel available, and a better carbon footprint overall. There is a well-developed science available to ensure the long-term performance, and we have field experience which are now greater than 50 years for critical applications, such as the Valcroze Dam in France. But deficient drainage is typically a root cause in the failure of man-made structures. Therefore, the geocomposite drains and filters must be properly designed, just like any other drainage material. You should not consider that there is less design needed using a geotextile filter than if you were using a sand filter. It must be designed, just like everything else. And there is a variety of products available on the market. And I love this thing. I found that recently, a little post in a magazine from the 60s, how to dispose of oil. At that time, digging a hole in the ground, putting some gravel and pouring the oil was the best solution available out there. What I read when I saw this cartoon, which was published as a joke on Reddit, I think, how will people see us in 6 years from now? Now we are laughing loud when we see that, but how people will see us in 6 years from now when looking back at how we are treating gravel, how we are basically consuming gravel broadly without much consideration on the availability. Cost is the only driver. I think that's something that we should consider. This is funny for us. What is going to be funny in 60 years when we look back at today with respect to gravel, to the consumption of gravel and aggregates? So that's really the end of my presentation. And I'm a little bit behind schedule. I'm sorry about that. But if anybody is interested, I'm happy to answer any question.
Thanks, Eric, for the really interesting presentation. Can you guys hear me?
I can hear you.
Okay, that's great. That's great. Yeah, we have a few questions online, and we are about 7 minutes behind schedule. Maybe we'll pick on 1 or 2 questions to answer, then I'll send the remaining questions to you so that you can answer it directly to the person that posed the question.
Yeah, sure.
Yeah. Can you also see the Q&A from your side? So
I just opened it. Opened it. So you want me to go through that? I see actually 5 questions, so maybe it's going to be not so complicated. One of them is a comment. Gordon Stevens mentioned that the Zoknok Dam did have a chimney drain. Fine, thank you. In full disclosure, I use this photo because it was showing clearly the piping mechanism. But I did not visit this dam myself. I think I got this photo from Kelvin Legge. I think he had it from JP Giroux. So it's a long path between the actual project and myself. It was only there to illustrate a serious problem. Second question, Jonathan Shamrock. Hi, Eric. Any comment on long-term durability of geotextile used in critical drainage application like in dams and landfills? Are there studies that you can point us to that addresses this issue? So for landfills, I think there are two components. First is the basal liner. And for that, I made a paper I think it was 2 years ago in Sardinia, where I present my opinion, which is that for basal liner, for drainage layer, which I installed on top of the primary geomembrane, the service life of the drainage component is actually not very long. In the example I use, it's about 18 months. Why? Because the more you put some waste in the landfill, the more absorption and evaporation you're going to get. So the quantity of liquid, you design the drainage layer for rain, for the 100 years rain or whatever. But after that, you will have materials which are going to divert most of this water from the drainage layer. And therefore, the service life of this drainage layer is actually not long. So we don't need to have 100 years or whatever we could expect for a German rain, for example. It's a very different situation. So that would be my answer for that. And for dams, there is nothing that I know except the first-hand observation of one project, which is over 50 years old. But I would assume that it is possible to obtain more information from manufacturers at some point because they have a history of projects. So I'm not aware of research done on this topic for dams and those critical infrastructures. So,
and Johan is away, Eric, so maybe I'll just send the questions to you directly after. And probably the last questions we can answer is from Jasper.
Jasper,
Yeah.
On the reinforced soil structure, you show a picture where the geocomposite was installed, leaving a space between them. Haha. So I learned this recently, actually. I was puzzled myself. It is for stability of the structure, because if you have a geocomposite on the slope everywhere, you have no connection between the soil, which is installed on top of it, right behind the wall, and the soil mat which is behind. So you must leave some space between the drainage component to make sure there is an anchor between the backfill and the native soil. If you don't do that, you're creating a slippery plane, and that can be very dangerous. So there is a very good reason for that.
Thanks, Eric, for the answers. Hopefully the webinars, I think it's really interesting, and hopefully it will be interesting for the audience as well. We would record it and put it up on our website so you can access it after, and also to go through some example that Eric has put up on the slides. So lastly, thank you, Eric, for really spending your time and spending an evening for ACIGS on this webinar. And I also would like to thank all the attendees for attending the webinars. So I'll see you guys in the next webinars. And yep, have a good day and have a good evening, Eric. Yeah.
Thank you very much. Yeah, good end of evening.
See you all.
Bye-bye.
Yeah. Bye.